Okay, we were trying to find the dimensions of the largest, what do we do? Largest isosceles triangle that can be inscribed in a circle of radius 4. Okay, I'm going to have you guys do some problems like this. There's some three-dimensional ones where it even gets a little harder, where it might be something instead of this, it might be finding the volume of the largest cone, say right circular cone that fits in a sphere of radius 4. Pictures are going to look pretty similar, but the formulas will be a little different. Okay, so what we said was to do problems like this, a lot of it has to do with how you do the coordinate geometry. Where do you put the circle, for example, on the XY plane? We want to set it up the most convenient way, and so we centered the circle on the origin, and then we drew ourselves this picture where the red triangle represented the largest isosceles triangle. We knew that we could orient this thing so one vertex was at the top of the circle, and then the other two were down here someplace. We did a little reasoning here, and we decided that there would be no sense in ever picking the pink triangle over the red one. They both have the same base width, right? But if you're going to have this wide a base on the triangle, why not have the extra height and push it down below the x-axis, right? So there would be no reason for us to ever even consider triangles where the y values that we chose were positive. Okay, they'd all be negative. If we look at the coordinates of these points, we know that we're going to be, the coordinates at this point I'm looking at right here, for example, would be x, y, where y would be some negative number because it's below the x-axis. And so if we're dealing with negative y values here, then we came up with a formula for the area. We said that the area would be 1/2 the base times the height, of course. The base had a width of 2x, right? That's x and that's x. So 1/2 times 2x is just x. And then the height, this was a little strange. We said the height was going to be 4 minus y. And we justified that by looking at a couple of examples. For example, we said, what if y were -1? Then we'd get 4 minus -1 would give us a height of 5, and that worked the way it was supposed to, right? If y were +1, then we would have gotten a height of 4 minus 1 is 3, which would have also worked. So we came up with this formula. There's our formula. I guess, what is that? Step 2? Step 1 was drawing the picture. Step 2 was coming up with the primary equation, the quantity that we're trying to maximize, which was area. But the problem there was that we had two independent variables. So we have to move on to step 3. We have to come up with a secondary equation that relates x and y. And the secondary equation we could either think of as being the equation of the circle. That's fine. The equation of the circle is x squared plus y squared equals r squared. That's the equation of a circle centered on the origin, right? And the radius in this case is 4. So x squared plus y squared equals 16. Or we could instead, they end up being the same thing. We could look at this in terms of maybe just a little right triangle. A right triangle that takes us from the origin down to this point x, y. We know that the width of that triangle is going to be x, the height of the triangle is y, and the hypotenuse is just the radius of the circle, so it'd be 4. Either way, we come up with the same thing, x squared plus y squared equals 4 squared. And so there is our equation of constraint, our secondary equation. And then we wanted to solve for either x or y and substitute. We decided that it's not that big a deal, but we decided to substitute for x because it was by itself out here as a factor. Can I get you guys to stop talking, please? Thanks. So we solve for x, and if we solve for x, we get the square root of 16 minus y squared. We're only going to take the positive one because x has to be a positive number. This is positive x, that's negative x, but either way, the absolute value, the value of x is positive. If we put a negative sign out in front, it'll make it negative. So we ended up with this formula, right? We're able to plug in for x, we can plug in the the square root of 16 minus y squared. And finally, after all that work, we get down to a point where we have the area, the primary function, trying to maximize area in terms of a single variable. And so now we can do some calculus. Question?
Okay, just a quick question. So 4 minus y, is that just from the area of x is equal to x times?
Well, that was what we decided the height of our triangle was.
Well, right. I understand. I just had to look at it again to say it out loud to myself. I get it now.
Okay, so 4, and then if this is a negative value of y, we're subtracting it to get a positive contribution to the height. Okay? Now, you could have, if you wanted to, you could have set this up so we could have called this negative y if we wanted to and let y be positive. But to me, that seems a little convoluted because this way, x and y really are, the coordinates, where it's a point on the circle. I think that's the clearest way to do it. Okay, so then we had to do some calculus here. Well, one thing we had to do is we had to establish what the domain was, right? And we said that mathematically, this thing could have a domain that went from -4 up to +4, right? Because the reason we said that was that we can't have a square root of a negative number, right? And so y would be limited there. If y were either more positive than 4 or more negative than -4, like let's say we put in -5, for example, 16 minus -5 squared would be 16 minus 25. That's a negative answer. We can't have that. So we're limited because of that rule, that mathematical rule, that we can't take an even root of a negative number. We're limited to this for our domain. But then we have to consider that we're not really doing this. It's not strictly a mathematical problem. It's a geometric problem. And so what would the values of y be for us? Well, we would never consider a negative value for y, right? Because the way we've set this up in our picture, our y is just the part that we're subtracting from 4, right? We're never going to subtract a positive value for y, are we? I think I said it backwards. We're never going to subtract a positive value from y. We're going to subtract only values of y that are below the x-axis. And so we could just go from 0, y equals 0, down to -4, right? We don't need to think of the whole mathematical domain. We can limit ourselves even a little bit more and just say that. Parts that make sense for us in our particular drawing. So -4 to 0. There's our domain. Now, finally, we get down to the last step, which in this case is probably the hardest one. That's the calculus. We've got this thing. Now we've got to go through and differentiate and find the critical numbers and see what happens. And that's where we sort of left off. Okay, what had we done? We said we applied the product rule, it looks like. We said the second factor times the derivative of the first plus the first factor times the derivative of the second, which required the chain rule. Left us with this whole big mess. Looks like we were in the process of factoring out like bases. We can see that we have like bases here. We have a 16 minus y squared to the 1/2 and to the -1/2. We can only factor out the smaller of the two powers, so the -1/2. And what did that leave us with? If I divide that away from the first term, I'm left with -1 times my base to the 1/2 minus -1/2. 1. Right? So we get 16 minus y squared to the 1. What about the other term? The other term, we've got this minus y times 4 minus y, and then this whole thing goes away, doesn't it? We factored out that whole thing. Okay? So that's what we get. Right? Would you agree with that? So then this goes to the bottom as a square root. On the top, we can combine some stuff. So on the top, what are we going to get here? We're going to get, if I distribute the negative sign, I'm going to get minus 16 plus y squared minus 4y. And then it looks like plus y squared again. If I distribute that -y. On the bottom, we've got the square root of 16 minus y squared. And so what does this turn out to be? Y squared plus y squared is 2y squared minus 4y minus 16 over square root of 16 minus y squared. Let's see, we can factor a 2 out of the top. And then, is the rest going to factor? Oh yeah, maybe it will. So we factor a 2 out, and we're left with y squared minus 2y minus 4. Can you think of two magic numbers that multiply to negative 4 and add to 2? Oh, 8. Whoops. Two magic numbers that multiply to negative 8 and add to negative 2. In other words, does that quadratic factor? I mean, multiply to negative 8 and add to negative 2. Negative 4, positive 2. So this one does factor. That's convenient. So we get a prime of y equals 2 times y minus 4 times y plus 2 all over square root of 16 minus y squared. So that's good. We got it factored. Are we going to try to probably do a second derivative on this one?
No.
No way. No way. We'll just use the first derivative test if we need it. Okay, so let's grab this. Oops. Okay, so where are the critical numbers going to be then? What are our critical numbers? Y equals, where would this equal 0? Where would this function equal 0? Okay, where the top equals 0, which would be at 4 or negative 2. And then the bottom would be undefined. It looks like only at the endpoints, at plus and minus 4, in our domain, right? So equals 0 here. This is where, actually I should write that down. Here's where a prime of y equals 0 at those places. And then a prime of y is undefined at y equals plus or minus 4. Okay, so in our domain actually only went from negative 4 to 0. So which of those do we keep? Negative 4 to 0. So we don't keep this one. That's not in our domain, is it? And negative 4. Oops, that should just be negative 4. Okay, so we'll make our table then and see what we get. So we have y area prime. And let's go ahead and let's put our domain on here. Our domain went from negative 4, square bracket, negative 4 up to 0. We had an interior critical number at negative 2. Yeah, it was a 0 of the first derivative. Negative 4 was an undefined first derivative. So now what? Yep.
Okay, what are we trying to solve?
The whole point of this was to find the dimensions of the largest isosceles triangle that can be described in the circle. So once we find y, we'll have to go back and figure out the x that goes with it. But that's easy to do because we have an equation of constraint here. We know x is the square root of 16 minus y squared. So x will be a freebie once we get y. But now we've got to we've got to do our calculus analysis on this thing here. So, what do you
Test
think?
points?
Say it again.
Test points?
Test points. We could put in test points if we wanted to.
-3 and 1.
Okay, -3 and -1. We could check the sign of the first derivative there if we want to. We've got the first derivative factored, so that's going to make it easy. If we want to evaluate the sign of the first derivative at -3, what do we get?
Isn't it just that, or, isn't it just like a regular equation that we start out with? Oh, never mind.
Well, I mean, we could. You guys, there's a bunch of things you could do here. What are some strategies? What I thought I think he's thinking about. I think what Ethan's thinking about is we could do the first derivative test on this point and see if it's a peak or a valley. We only have 3 points here, though. What's something else we could do? We know that there's only one critical number, and then I've got my 2 endpoints. So what's another thing we could do that would be fine? We're just trying to find where the area is the biggest, right? Wouldn't you agree that the only place the area could have a maximum would be either at one of the endpoints or at a critical number? Those are the only possibilities, right? So we could just evaluate the area function at each of those 3 places and see who wins. That's another thing we could do.
I think zero's gonna
We'll see. We'll see. Or we could do the first derivative test. Either way, the first derivative test, in a way, let's see. What's our area function look like? We never really got it factored, did we? The area function, we didn't have a need to. Well, there it is. I guess we do. Okay. The disadvantage of that is that we have to actually plug in those numbers. I wouldn't do it that way. Remember I told you earlier it's easier to work further down in the table? The reason being, if I plug in these values of y, that's a pretty ugly function. I have to come up with answers. If I use the first derivative test, I don't need answers. All I need are signs. Is it positive or negative? That's easier to find. If I want to find the sign of the first derivative at -3, well, what do we get? At -3, I get a positive times negative times negative times, or divided by positive. So that's going to be a positive on the top divided by a positive on the bottom is positive. Okay?
It's a negative.
So get rid of those.
It's a negative.
So we get positive sign of that derivative. Now what if I go at -1? See the same thing. At -1, I'm going to get positive for 2, negative, positive, positive. So positive times negative is negative in the numerator divided by positive in the denominator. Negative. Okay, so that tells us that this is a what then? If the first derivative is going from increasing to decreasing, what is that? No, it's a maximum. Okay, in fact, we know it's a 0. We know it's a nice. What now? Oh no, this is just the tangent. This because it's a 0, because the slope is 0. It's got a horizontal tangent, and it's a nice rounded mountaintop. Okay. So we know it's a peak. The only other critical number we have is clear out here at the end point. And so sure, mathematically the function might turn there, but who cares? Because that's the end of our domain anyway. So is it possible that if there's no other place in our domain between the endpoints of our domain where there's a critical number, could there be any other place that's higher than that? Yeah, well let's draw it. So we know we've got something going on like this. Now we don't know where this is happening, but if we're calculating area, we don't know what the areas are, but if we're going from 0 down to -4, at -2 we had a peak, right? The only other critical number is down here at -4, so then we know that between -4 and 2 this thing can't have another peak or a valley, right? So it's going to do something like that. Same thing here maybe, right? We know that between 0 and -2 there are no critical numbers. In fact, 0 is not a critical number, right? So it can't have a valley so it could turn around and start pointing upward. Keep in mind that peaks and valleys are turning points. That's where the function changes its behavior, right? So we know that in this direction, there can't be any other place higher than that. In this direction, there can't either. Once we get to this turning point, maybe the function goes up and does something weird, but we don't care because that's out of our domain. The domain stops at -4. So within our domain, doesn't it make sense that then that has to be that relative maximum is the maximum. That's the absolute maximum.
Yes.
Right? Okay, so we know that that's our winner. That's our winner. So y equals -2. If y equals -2, we can go back and find x. Right here. So if y equals -2, then x equals the square root of 16 minus -2 squared minus 4. Square root of 12. And we got it. The height of this thing then would be, now we have to interpret this. The height is 4 minus y, right? So the height would be minus -2 is 6, right? And the width would equal 2 times x, and x we said was the square root of 12.
Well, 2 times that.
Because that's x,
Gotcha.
and that's x, right? So we just get 2 times the square root of 12 is the width. We got it. That's how big those are the dimensions of that triangle. There's a lot, I mean, there's a lot to that problem.
There was a lot of that.
Yeah.
I believe I saw it.
Okay, I think the thing to do now is you just got to kind of keep pushing through this assignment, and some of them are going to be easier, some are going to be quite a bit harder. So, I mean, not harder than this. They don't really get much harder than that. That's about as hard as you could get. But, well, there's a couple that are about that level, though. So, we're probably going to have to come back and talk about these some more, but I think you got to kind of push through it and work a little bit first. So, let's go do that.